Manually grading D3 visualizations is a challenging endeavor, and especially difficult for large classes with hundreds of students. Even for a simpler bar plot visualization, manually grading it requires a combination of interactive, quantitative, and qualitative evaluation, with tasks such as verifying the correctness of data bindings and visual encodings, testing interactive elements, and determining if a visualization's overall layout and spacing is appropriate. For a large class with hundreds or thousands of students, such manual grading becomes extremely tedious and time-consuming. To address these challenges, we present VisGrader, the first of its kind automatic grading approach for D3 visualizations. VisGrader renders a student's visualization in the browser and then automatically interacts with it. Gradable elements, such as data points, visual encodings, scales, and plot dimensions, are extracted from the student's code that generates the visualization. The autograder generates a tailored solution plot and compares with the student's visualization. Then, the student receives feedback to improve their visualization based upon rubric requirements using the Gradescope platform. In a typical use case, a student implements a visualization according to a description and an assignment rubric, and then uses Gradescope platform to submit their source code files. VisGrader runs the visualization in its own browser and grades it using a suite of test cases that match an assignment rubric. Test cases are generally organized to grade the appearance of marks, scale and data positioning, and interactivity. We also include some purely advisory test cases that perform some pre-checking to make sure that all of the required components of the visualization are present before grading begins. After running the test cases, scores and results are returned and immediately displayed to the student so that they know which test cases that they passed or failed. After the student makes changes to their submission, they may resubmit their visualization as many times as they wish to try and achieve a better score. In practice, we find that even for detailed instructions, students will always make different, and not necessarily wrong or incorrect choices in how they implement their visualization. We designed VisGrader to be flexible to accept differences in design choice that are still valid within the assignment requirements. Now, our challenge becomes how we extract the gradable elements from different designs. To accomplish this, we use a lightweight underlying structural specification that ensures that all designs have an equivalent underlying structure. When a visualization is rendered, the HTML structure is extracted, and a tailored student-specific solution is generated for comparison with the student submission. The tailored solutions are used to compare and grade the student's design against the rubric without unnecessarily constraining differences in design. For example, VisGrader will use the size dimensions of the student's visualization and generate a tailored solution that generates the expected X and Y positions of the data. This allows us to grade whether or not the data are positioned correctly in different scalings of a visualization. Similarly, the tailored solution will generate the expected count of data points and validate that the student's implementation has an equivalent amount of data points. Another challenge is grading rich interactivity for a D3 visualization. Let's say we have a node link diagram that has several interactive behaviors. If we hover over a node, it should change color. If we click and drag the node, it should become pinned and retain a fixed position and highlighted color. To unpin a node, we can double-click on it and it resumes its original layout and color. Grading all of these manually is extremely time-consuming, even if we only tested a few nodes. To motivate how we might grade this automatically, we observe that interaction events within a browser result in changes to the document object model. To capture these changes, we observe the change within the HTML attributes of an element we're interested in for each interaction event. In our node link diagram, we store the fill color of a node and observe that it changes when the user hovers on it. When the user clicks and drags on the node, we can observe that there is a change to the XY position. Finally, if the user unpins the node, we can see that the node XY position resumes normal layout and that the fill color returns. We can grade all of this interactivity scalably with our adaptation of a browser automation package called Selenium to auto-grade complex sequences of interactive events through the use of action chains. Selenium's action chains allows us to grade interactivity at a large scale and give instantaneous feedback to students on the function of their visualization. Now that we've given an overview of how auto-grading is accomplished, let's take a look at how we use the results of auto-grading to help the student improve their design. We learned that returning the limited feedback of a generic test case output that only returns an index error or displays limited information is not as helpful in a learning environment, and sometimes causes frustration among students who are trying to isolate a problem. To make the feedback more helpful, we began designing test cases that provide multi-level feedback in an effort to help the student resolve complex programming issues. Now our unit testing design provides increased information about a particular rubric item being evaluated. As an example, we will display the actual information found by the autograder versus the expected result when a test case fails, along with possible fixes or resources that can help them. VisGrader had impacts upon both the students and instructor staff. As a result of using Gradescope for submissions, students have a greatly simplified and transparent workflow as they complete work on their assignment. Students are able to see their scores immediately instead of waiting for the grading session to end. One example of improved learning is evidenced by the quantity of student questions on Ed Discussion, the course's discussion forum. We saw that the number of questions decreased by 31%, from 1,965 posts to 1,356 posts, for a nearly equivalent enrollment size, when we compare Fall 2020, which was the last semester before VisGrader was deployed, and the most recent semester for the online section of the course. We observed students completing more error discovery on their own and then helping others, allowing students to get answers and leveraging the economies of scale that exist in a large class size. Using VisGrader resulted in a reduction of 400 teaching assistant hours spent on grading effort every semester. Before this, a grader would typically spend 5 minutes to grade one submission. For a class size of 1,100, this requires approximately 100 hours or 5 part-time TAs per visualization. Scaling this to 4 D3 visualizations in one assignment required close to 400 hours or 20 part-time TAs who focus only on grading. The autograder eliminated 98% of regrade requests. These requests resulted from grading errors that arise from manual grading workflows, such as the manual tabulation of scores or having to reconcile student and instructor development environment discrepancies. As a result, we have freed up TA hours that were previously needed to regrade these assignments. In response to the reduction in required TA grading hours, we redistributed TA effort to support the student questions through office hours and increased interaction on Ed Discussion. TAs were able to provide higher quality instruction and focus on more qualitative questions rather than repetitive routine questions. In addition, the instructional staff was able to spend more time collaborating and improving the autograder from semester to semester. In closing, we discussed limitations of VisGrader to inform our plans for improvement and future work. We acknowledge that there could exist tendencies for the students to focus too much on passing test cases to get the maximum score and move on without further exploring learning in the design space. Therefore, learning correlates with quality and coverage of the test cases used. For this reason, we continue to strive to design test cases that provide learning opportunities that facilitate formative improvements. While we emphasize best design practices in classroom teaching, we currently have limited test cases that provide feedback on design choices. In the future, we want to increase focus on assisting students in design choices by helping students design charts that are accessible. For example, having a colorblind safe scheme for colors, a proper color contrast, and font sizes. While VisGrader has not been used for grading other libraries, the method could be adapted to grade other visualizations that use HTML, CSS, and SVG. We want to see adaptations of VisGrader that could make it possible for instructors to teach different visualization libraries, such as Observable or Vega Lite, at a large scale, and autograde them using our method.